So in this session, we'll look into the design of angle struts. So these are the members within the truss elements. So normally they are members of a truss which are in compression. We call them as struts. So what IS code tells about designing the angle struts? We have already seen about design of compression members such as columns and all. In section 7.5 of page 47 or in page 47, this particular design of angle strut has been mentioned over there. So if you go to this section, it deals with single angle struts, and what you come across is these angle struts may be loaded concentrically or they may be loaded through one leg only. So when you have a end connection arrangement such as the gusset plates and the additional members if they are provided, so that the member, that is the angle section which is provided as a compression member in the truss, if it is carrying the load applied through its centroid, that is concentric loading if it is having, then you can proceed with the design what we have dealt earlier, that is as per 7.1.2. In case if the load is transmitted or resisted through one leg only, or loaded through one leg only, then this 7.5.1.2 has to be followed over here. What this 7.1.5.1.2 tells us is to calculate the non-dimensional effective slenderness ratio. Here what is considered as the equivalent slenderness ratio, lambda e. So we are no longer dealing with that lambda in case of this angles loaded through one leg. Instead, we'll go for calculating this equivalent slenderness ratio, lambda e. So this lambda e is expressed in terms of these constants k1, k2, k3, and another two parameters, lambda vv and lambda phi over here. So k1, k2, k3, they have been given in this table 12 of the code. So these mainly depends on what is the end connection, what is the number of bolts provided at the ends, and also on the fixity condition. So this fixity condition is expressed as fully fixed or hinged, and in a number of bolts it may be more than or equal to 2, or it may be one single bolt only. So depending on these two the things, that is what is the number of bolts in the connection that have been provided, and what end connection you come across, that is whether it is a fixed condition or whether it is a hinged condition. Depending on that, we can get these k1, k2, k3 factors. So these are the constants what have been given in this table number 12 over here. And other than this, we have these two more parameters that have to be calculated, that is lambda vv and lambda phi. So lambda vv, lambda phi have been expressed by this equation. So lambda vv, it is L by RVV divided by epsilon into root of pi square E upon 250. Here, and just note a correction over here in this code, this term within this root, it is printed as epsilon, but it is the Young's modulus what is there. It is E, modulus of elasticity, or the Young's modulus of the steel. So rightly speaking, this lambda VV will be L by RVV upon epsilon into root of pi square into E divided by 250. Similarly, lambda phi is B1 plus B2 by 2t divided by root of epsilon into root of pi square E upon 250. Okay, now let us look into these terms over here. L indicates the center to center distance between the connection, and RVV, radius of gyration about the minor axis. So this is the radius of gyration about the minor axis of the angle section. If at all, if it is unequal angle section, then you will have a major axis and minor axis. So what will be the radius of gyration about that minor axis has to be chosen over here. And further, here lambda phi, here you have b1 and b2. These are the width of the two legs of the angle. So b1 and b2, for equal angle sections, b1 and b2 will be same. T is the thickness of the angle section. The other terms what you come across here are all constants. that is pi square modulus of elasticity of steel, and epsilon is the ratio of 250 upon Fy and its square root of 250 by Fy. It's the ratio of the yield stresses. What is the yield stress of the material what you are considered? 250 divided by that square root. Take the square root of that. So from this you will be able to determine what is the equivalent slenderness ratio now. Now instead of determining lambda what we used to do earlier, we'll go ahead with this lambda and then calculate what is the permissible stress in compression FCD. Either you may follow the equations, that is calculating the stress reduction factor, and then go for calculating FCD. If not, you can even go ahead with using the tables 8 or table 9. Table 8 gives the stress reduction factor, whereas table 9 gives the directly the permissible compressive stress over there, FCD. So these tables can be used here. So when you are dealing with angle sections, this is mainly for angle struts. So when it is a question of angle sections, the buckling class will always be C, irrespective of the axis. Buckling class given is in table 10, you can verify that. So that buckling class given is C, whether it is X, Y, or any other axis. About any axis, the buckling class comes out to be C. So we'll be, if you are using the table, you'll have to go with 8C or 9C table. In case if you are using the equations alpha value, choose it for buckling class C over here. So this is how the angle struts have to be designed using the equivalent slenderness ratio given in this clause of 7.5.1.2. Right. This was about the single angles over here. Right. We may also have double angles in the trusses, that is when angles are provided uh, attached together, either back to back or the two legs together. So when you have the double angles being provided over there, then the load may be considered to be applied axially. In this case, this 7.5.2, this is about double angle struts. So there may be a single angle strut or double angle strut. In case if you have double angle strut, then what it says is the load has to be considered as applied axially. So that is the condition. And what is the effective length for this in that case is it varies from 0.7 to 0.85 times the distance between the connections or distance between the intersections. So depending on the what is the fixity condition, choose this value of k, whether it is zero point 0.7 or 0.85. So if you have a very rigid connection at the end, go to for choose taking this k as zero point 0.7. Else you can take up to 0.85 in case if it is does if it is not having sufficient fixity at the ends. Okay. Let's take up one of the problem on this, that is on a single angle strut over here. So what has been given here is to calculate the compressive resistance, that is the load carrying capacity under compression of angle section ISA 200 by 200 by 20, and assume that the angle is loaded through one leg only. It is said that the angle has been loaded with one leg only, and when the conditions have been mentioned here, it is connected by two bolts at the ends. Okay, it is connected by one bolt at the end. Third is when it is provided with the welds at the ends. So under these three conditions, we need to find out what load it can carry. So since it is a single angle section and it is told that it is loaded through one leg only here, okay, if at all if it is not clearly mentioned in the problem that it is loaded through one leg, or it is having a concentric loading, and if it is given that it is single angle section, then it is better you go ahead with finding with the assumption that it is loaded through one leg only, because this will give you the lowest load carrying capacity when it is loaded through one leg only, right? So here the torsion will come in action when it is loaded through one leg, so which will reduce the load carrying capacity. Okay, so we call that as a flexural torsional buckling that will take place in the member. Right, coming to our problem, first case when we have the bolts, two bolts have been provided at the ends. So here certain amount of fixity will come when it was about two bolts. It depends on the designer what we assume over here. So my assumption is I am going to take the ends to be fixed over here. When two boards have been provided, I'll assume that as fixed. In this problem, I'm going to calculate that relatively. The my next case is one board. So here I'll go with the assumption that it is having fixed ends. Two boards, fixed ends, right? So what we'll do is first is we'll determine K1, K2, K3 factors. So two boards are equal to or more than two boards. This is my case, number of boards. Then I assume that the end connection is fixed. So K1 is zero point 0.2, K2 is 0.35 and K3 is 20. 0.2, 0.35 and 20. So these have been taken from this table 12 of the code. And what is the ratio of this epsilon? Epsilon is 250 upon Fy, and root of that square root of 250 by Fy. Since Fy is 250 MPa, that is here 250 Newton per mm square. So this comes out to be 1.0. If not given, don't worry, just go ahead with 250. This is the common yield stress what we adopt over here for Fe 410 grade. This will be the yield stress. So epsilon comes out to be 1.0. Now what about the lambda VV value? So lambda VV, the member length has been given as 3 meters. I'll assume this to be the distance between the centers of the connection. So 3000 divided by RVV. So RVV, you'll get it from this steel table. This value has been chosen from the steel table for this angle section ISA 200 by 200 by 20. So L divided by RVV, this divided by root of pi square E upon 250. This will give us lambda VV as 0.859. Similarly, lambda phi. What about lambda phi? It will be B1 plus B2 divided by 2T, whole thing divided by epsilon into root of pi square E divided by 250. So that will be here B1 plus B2, since it is ISA 200 by 200 by 20 equal angle section. So B1 and B2 will be equal to 200. 200 plus 200 divided by 2T. 2 into 20. T is the thickness of the angle section. So divided by 2T. And this whole thing divided by root of epsilon into root of pi square E into divided by 250. So for this, the lambda phi value comes out to be 0.1125. 0.1125. We got lambda VB as well as lambda phi. Now equivalent slenderness ratio, that will be K1 plus K2 into lambda VB plus K3 into lambda phi square. K1 plus K2 into lambda VB square plus K3 into lambda phi the whole square. So this is 0.843. So we will be taking this as our non-dimensional slenderness ratio lambda. So here the value of phi has been calculated here using the equation. Phi will be equal to 0.5 into 1 plus alpha into lambda minus zero point 0.2 plus lambda the whole square. So lambda E has been chosen here. In place of lambda, lambda E has been chosen. Buckling class, it belongs to angle section. They always belong to buckling class C. For buckling class C, alpha value is 0.49. So this gives us phi value as 1.013, and FCD, which is Fi upon gamma naught divided by phi plus phi square minus lambda E square raised to zero point 0.5. So this will be FCD value, which is comes out to be 138.56 Newton per mm square. So from this, the load carrying capacity, what we have is area, the FCD, A into FCD. So area of the section in what is the area of section of that ISA 200 by 200 by 20. Okay, so that into 7640 is the area, and this is FCD. So that totally gives us 1058.6 as a kilonewton as our load carrying capacity. So this is for case A, when two boards have been provided and we assumed that the end condition is fixed. Okay, even you can go with assuming that end condition is hinged also. Okay, with the same number of boards, end condition may be assumed to be fixed or end condition may be assumed to be hinged over here. And even after finding out for these two conditions, if you want to have somewhere a intermediate restraint, neither completely fixed nor completely hinged, if you want to go with that calculation, then first go for finding for fixed condition, then for hinged condition, then you can interpolate the two value of load carrying capacity for whatever fixity condition you want. We can take even the average of these two load carrying capacity also, if at all, if I assume partially fixed. Okay, so that is how this table and equivalent slenderness ratio has to be used in case of single angle struts. Okay, that is about case A, when fixity condition is assumed, fully fixed condition. Now coming to second case, it is said that single bolt has been provided. Okay, it is connected by one bolt. Okay, so here we have the single end condition, sorry, single bolt condition. And when you have single bolt, there's here we can easily make a judgment that if single bolt is provided, it behaves as a hinged end. Okay, so I may not be confident in taking that as a fixed end condition. So what I'll do is hinged. I'll assume that the end condition is hinged and number of bolts provided is given as one bolt. So in this case, k1 is 1.25, k2 is zero point 0.5, k3 is 60. And lambda e, what happens to lambda e? Our lambda vv and lambda phi will remain same because the section has not changed. Lambda vv and lambda phi, so they are going to change only in case the properties of the section will change. Okay, that is rvv, b1, b2 and t. If they are changing, then this lambda vv and lambda phi will change, else they will be same. So with the same value of lambda vv and lambda phi, if we go for calculating the equivalent slenderness ratio lambda e, that is k1 plus k2 into lambda vv square plus k3 into lambda phi the whole square, lambda phi square, then it this comes out, for this particular case it comes out as 1.542. So phi is equal to using the equation, that is zero point 0.5 into 1 plus alpha into lambda e minus zero point 0.2 plus lambda e the whole square. This gives us as 2.08. Okay, so FCD on using the values, what we have is FCD comes out to be 218.18 Newton per mm square. Sorry, this is this should be actually 250. So try using the 250 value here. 240 has appeared and calculation is for that itself. Take it as 250, fi as 250 and recalculate this one. So FCD comes out to be 65.72 Newton per mm square. And the load carrying capacity PD, that is FCD into E. So this gives us a load carrying capacity of 502 kilonewtons. And third case is when welds are provided. So when you have welds being provided, they offer full rigidity of the joints, complete fixity of the joints. So it is as good as our first case with bolts more than two and fixed condition. If at all, if you have welds being provided at the end connection, then directly you go for with this one. That is uh, first case, more than two bolts and fixed condition. Okay, so this is what the condition is. This is just like our previous case A, wherein we got the load value of 1058.6 kilonewton. In the third case also, with that assumption, we'll have PD as 1058.6 kilonewton itself.